So if nobody screams, I will start now. So thanks to everyone here to listen to this presentation. The method that I will be presenting today, that I've been working on with a few colleagues from Saint-Gobain, is called Cube. So I will try to explain what it is, how it works, how we try to validate it, a few results, and see what is in the near future for us. First, what it is. What we want to do, to be clear, is we want to do basically the same thing that a coating test does, but faster. So faster, we would mean hopefully less than 3 days of total experimental time. That was the aims at first. When we started this project, we knew that that could be complicated, so we accepted Earth sensitivities. Well, we didn't aim to be very, very, very accurate, let's say, but we hoped to have maybe 15% uncertainty. That was the goal. And as I said, the result is the heat loss coefficient as in coating. So as Staff already said, you can think of it as an attempt to measure the same thing as the coating does, but faster. I would add, though, that it only measures the heat loss coefficient, and it's not right now possible to have very accurate values of, for example, solar factor or something like that. It's not what we're trying to achieve. So first, Cube means quick Q value of buildings. It's been patented by the Saint-Gobain group as a dynamic diagnosis method, and it's actually quite simple as to put into place. It's a dynamic method, meaning that we actually heat the building for a few hours, and then we stop the heating for a few hours. Below the text, you can see what a standard test looks like. For example, we'll be coming maybe in the afternoon, installing our material, then test, put some heating during 24 hours, then stop the heating, and then have a second night where the building is cooling, and we can come back, clean everything, and we are done. The heat loss coefficient that we will be calling K in this presentation is then a function of three things: power, temperature, and temperature slopes. The temperature derivates in function of time, if you will. So there's only these three informations that we need. To give a little more detail, first let me show you what a real test looks like. This is an experimental result done in the exact same method than previously shown. The temperature, so in blue the external temperature, in red the internal temperature. It's an average value of several temperatures. I will go into experimental details later. And the green line I'll explain a bit later. So what we do is make a very, very strong hypothesis. So at first, you might think this is silly. So the point that we will try to make is explain how this hypothesis holds, and this is the main goal of our validation process. So our hypothesis is that after a few hours, the temperatures inside the building vary as if the building only had one time constant. So this is the first few hours. There's a first period, the first dynamic period, and then after that, when you see the green line, this is a fit of the red curve with only one time constant. So it's a very simple exponential. So what we see here is that after about 5 hours, our internal temperatures actually does behave as if the building only had one time constant with a single exponential function. Not the same for heating and cooling, of course, but that's not the point. So if our hypothesis holds, then, as I said, temperatures follow a single exponential function of T. This it's even simpler than the equations that Geert presented. If we put this into equation, we only write C, the inertia, times the T. Oh, I forgot one thing. divided by the small t, of course, so multiplied by the temperature derivate is equal simply to the power minus the heat loss coefficient times the temperature difference between inside the building and outside the building. So we only apply that for both heating and cooling periods. So for example, these here will be the period of analysis. I will explain also later why we take this period. And as a direct consequence, because we have two unknown, K and C, we just take C out of the picture. We don't really want it. And we have two periods, and we get a rather simple equation for K, the heat loss coefficient. So as you might think, this is something that can be calculated, but it's very complicated to know if it has any relationship with the truth. So that will be what I will try to explain. But first, I will go through the experimental process. So the difficulty in this kind of setup is to have a very good knowledge of the inputs. You have, in those previous equations, quite a few variables that you want to know. Of course, the temperatures inside and outside can be easy to measure, but the power becomes more complicated. We want to have, as possible, everything has an electrical heating, easier to measure. Of course, it's possible to heat with other sources of power, but it becomes usually less accurate. You have conversion factors and everything. You don't want to just take the heating, put it on, and say, okay, this is, for example, 2 kilowatts heater, so I will calculate with a 2 kilowatts value. You really want to measure the power. We actually realized that measuring, for example, with several systems like amperic, I don't know the term in English, well, the measurement of only the intensity will not be enough because the network tension can be variable. So you want to have a real measurement of the power, and then you will have a good information. But you also want, in the same time, to reduce the unknown power sources. The first thing to do is only use the night periods for analysis, and of course, take an empty building. So if we come back to the previous curve, it becomes more clear why we took these periods of analysis. We basically wait the latest possible time before the start of the day to put an analysis period during the night. Here you are. So this is what we take. Of course, the building is empty. We measure all electricity sources that cannot be stopped. For example, if in-house there's a fridge with food, we'll try not to turn it off, but to measure it. And we try to close all air vents. The house will be put as in a blower door, pressurization, that's right. This makes it possible to not have the influence of a very high infiltration losses, but I'll come back to this point a bit later. This is a dynamic method. This is not like the co-heating test, a static method where you just put all the temperature at the same values and wait for some time. You heat everything and you measure every temperature at the same time. The problem is that you will put constant powers in the house and you won't have temperature regulation. So it's possible to have high temperature differences between rooms when you start the heating. This is an example of one of the first steps we actually realized when we started to develop the method. If you don't do it properly, some rooms will be heated by 1-2 degrees when some other will be at 4 or 5 degrees. And if you want to make the hypothesis that your temperature is basically homogeneous in your building, then you can't. And so the averaging that you want to do is problematic and can lead to rather high errors because then it's related also to where exactly you put your sensors and everything. So what you want to do is manage to have some kind of homogeneous heating and not just for example, the heating system that is used during a co-heating system will not be adapted for a cube test. So you'll have a specific heating system. Sometimes possible to use, for example, a homogeneous volume heating or surface heating, for example, by using the HVAC system of a house, if you can accurately measure the power. We've already done tests with underfloor heating, which can work very nice also. It makes the temperatures very homogeneous in a building. Also, same thing if you can manage to measure properly the power. What we found is that most of the time it's easier to use not the heating system in the building, but always the same one that we take with us. And we try to use, instead of a few sources of high power, a high number of low power sources. At best, we use low radiation to heat the air rather than the walls to be close to what the U value of the building is. And we try to keep the conductive heating low so that it's also a difference with co-heating tests. We try not to mix the air, so not to have too much internal convection. The solution that we found is using some kind of heating mats first for the low power, and the trick we found was to put them vertically as in the picture. In this way, although it might seem a bit funny, it actually enabled to have a real nice reproducible heating of the air without interference of the ground. If you put the mat horizontally on the ground, some of the heat will go into the ground, and the value that you lose that way depends on the way the mat is put. So you have reproducibility problems. So if you compare the figure here, if you can see the mouse on the right, with the very high temperature differences, with what we managed to do with this test, then you get that. This is an example of the homogeneity that we managed to get with the vertical mats. These are tests done in a house which has 2 floors. We've done 3 cube tests that you can easily see. It was, I think, 2 years ago, over a period of 10 days. During test, we were just letting the house cool down for maybe 1 or 2 more days, so that we did not reach too high temperatures during the day. We have 9 temperature sensors in the 2 floors, and what you can see is that if your heating mats are put rather properly inside the building, it gets much easier and much more accurate to average your temperatures. You might want, if you prefer, to average the temperatures per floor and do a cube method per floor if you know your electrical power per floor, and then add your thermal losses per floor. It's just, when we tried the 2 different methods, it didn't really change anything. So, but anyway, what I want to say here is that the cube method can work very well, but you need a specific heating system to make it work nicely. Now, that being said, when we managed to get our method working properly, then we started a validation procedure. The principle is, of course, comparison with a reference value, which is a very difficult thing to do, because a reference value, we did not want to compare it to an estimation. We wanted a real reference of actual in situ performance, not an estimation, not like a calculation, not a prediction. A real other measurement of the real losses. We want it to not be occupant dependent, of course, and this is difficult to get. But now that you've seen 2 presentations on co-heating tests, you will understand that we have used co-heating tests as a reference for our methods when we could for all standard buildings. For what I call non-standard buildings or specific buildings, we tried in some cases to use steady-state conditions. Steady-state conditions being contrary to the quasi-static co-heating test. Real static tests where all temperature fluxes are stabilized. It only works for numerical validation, the same way that Guillaume presented the numerical results. I don't remember with what program he did that, but we did it with the same thing with chances. It was easy for us to get a building, to have the real heat losses, and to make, a bit like he did, measurements all around the year. Well, virtual measurements, of course, but I don't want to get into the details of the numerical validation that we did first before the main experimental ones, but all our cube values had rather low error. I say inferior than 15%, but it's usually much less than that. And the other thing is, as already presented by our colleagues from LMU, we tested our method in the energy house in the University of Salford. I will come back to that. So I was talking about the grading test that we did in near Paris in bungalows that are rented right now by the Saint-Gobain company. We did, as a reference, 4 weeks of grading, 2 weeks at one internal temperature and 2 at the second one. We measured the 2 values. We had rather high uncertainties on the results for both of them, but the differences we found could be very accurately explained by the wind speed, which changed a lot during the different tests. So when we renormalized the heating coefficient, the heat loss coefficient by using a supposed wind speed of 4 meters per second, then we get a reference heat loss of 32.7 plus or minus 0.9, which means that the variable wind speed explained a lot of the uncertainty. If we when we managed to fix that in the model, then the results became very accurate. I wanted to add that because the bungalows are very light structures, very small, etc., 4 weeks of grading might be equivalent to 2 or 3 months of grading in a standard heavy house. So this is, I think, a very accurate result. So we compared it to our own cube test, that because we have bungalows just near the buildings where we work, we could do a lot of them. And as I said, because the buildings are very light, we could do what was not done at first in real buildings, but test in one night only. You can see on the right, these are experimental results. I know the red curve might look a bit too nice, but it is an experimental result. So 4 hours heating, 4 hours cooling, you have 8 hours. The black lines, of course, are the calculation of the slope that we take for the analysis. The colleagues who worked on this part of the project did 25 tests, and the reproducibility showed a value of, well, an average value of 22.7 also, with a bit higher uncertainty or dispersion rather than for the grading test of 2.6. So you can see that the value itself is the same than previously. I would not say that it means that we have a 0% error. We'll just, of course, part of it is luck or things like that. The 2 methods have their own uncertainty, but I would say that it shows that the estimation is still very, very good. Another way to see that is the worst values we got were 28.5 and 38.5, which are less than, I think the worst is about 17% difference with our average value, which is also our reference value. So the conclusion, sorry, is that the comparison between the 2 methods shows both very close results, and also, I think it's very important, no real outliers. So we conclude on this small building that the measurements are quite accurate. Then we also, as I said, went to the University of Salford. I'll take a minute to explain a bit more what it is for those people who don't know here. It's a typical 1910 terrace property from the UK. Oh, and by the way, I thank Richard Fidden, who should be here listening to that for this part of the presentation. So, as I said, it's a typical terrace property from the UK, which we assume to have gone through a few reasonable modifications through the years. it has been put into a well-insulated concrete chamber built on a solid concrete base. And the most important is that around the house, you will have a chamber cooled by condenser units with heat pumps and especially very nice 0.5 degrees accuracy in the control. And you can change your external temperature of the house from -14 to 30 degrees. So it makes it possible to reach steady state values with very stable temperatures and fluxes, which makes that a perfect reference, we think. And we think it's the only such place in the world, at least it's the only one we are aware of. So we guess that it makes it a very, very useful experimental setup. This is an example of a steady state test. We put a constant power in the ground floor, in the first floor. We let the power for 4 or 5 days, and you can see between the two dashed blue lines, which represent 12 hours, very well, we think, stabilized values of temperatures with which we can estimate the heat loss coefficient of the house. The green lines in the bottom is the regulation of the external temperature. So with this method, we did actually three tests on 2 cases, with and without insulation in the attic. It's like a small refurbishment. If you look at the numbers here, what you see is, once again, very nice comparison. The maximum difference that we got between our measurement and the steady state values was only 7%. So these are examples. I would have a lot of more of them to show, but of course I have to limit myself for now. I will just go through a whole lot of other parameters that we checked either experimentally in specific experiments or numerically, just to say that the results of a few things. So insulation level, climatic conditions, influence of the season, summer, winter, the type of wall structure, and the infiltration or ventilation rate. So first, about the insulation level. We checked in several houses or several configurations in the houses, from almost non-insulated, like in Salford, to quasi passive houses, and in all cases we had the same quality of results. Considering the climatic conditions, the way we see it is that we want to make a test that is rather easy to do in practice, so we don't want people to have to get to a house with a weather station. So for us, the impact of climatic conditions will be linked to reproducibility. So usually when we take the same buildings and measure day after day after day after day, usually we have about plus or minus 10%, which is mostly due to the climatic conditions. I would add also that if your temperatures vary quite a bit, this variation might not always be a mistake. It's at least half of it, I'd say, is because the real thermal losses change from day to day. Then what we measure do change too, of course. So part of this variation is due to the modification of the reference value we're looking for. Part of it is simply the error we get by the measurements. And of course, houses with lower insulation or higher infiltrations are more sensitive to climatic conditions. So this is sometimes for very badly insulated buildings, it can start to be a problem. We actually measured some houses both in February and August without measuring any significant difference, which was a bit surprising to us, but it was not, the difference might not be superior to what you might measure from one day to the next, let's say. We also measured the influence of the wall structure, mainly by looking at internal insulation, external insulation, and kind of mixed insulation or no insulation, of course. And we found no difference. No, that's not true. We found differences, but it can be applied on every different conditions, but external installation might be a bit more complicated. It would be difficult to explain all the differences in such a short presentation. I will just say that internal insulation, then we will be we can be faster, more accurate, etc., etc. Now, a short point about infiltration and ventilation rate. What we measure is the heat loss coefficient is an estimation of total losses, infiltration and transmission. By itself, the method cannot differentiate these two aspects. As the co-heating test, but as other people before me shown that, for example, I think Geert said that they were making measurements of with a blower door and tracing gas and stuff like that. We tried to do this kind also of estimations, but it's something else. The method itself, the cube method itself, cannot do this estimation. So if you want to have them separately, you need to do something else. But what we think is our estimation of the total losses are accurate. The estimation that we can make of maybe only transmission losses, that might be a bit more complicated. So now I'm coming to the conclusion and perspectives. As you I hope I've convinced you, our method is a fast and reliable building energy diagnosis method. Right now, it's not that that it doesn't work or stuff like that, but it has a few constraints or a few limitations because we didn't have time to do everything we wanted. So what we know is that the experimental setup and the data processing are very easy, but it requires very specific material to be done in an optimal way. For example, if any of you want to try the test, I advise you to contact us so that we can help you put it into place, because otherwise what you probably will do is the same that we did when we started, is measure something that is completely useless, right? Really, it took us some time to get really reliable results. As I said, it gives the value of the total heat losses, and to repeat myself, it's been patented by Saint-Gobain. So if you want to do a few tests for research, I think you can freely do so. But if you want to make the measurements for money, then you have to go through us. But I'm not a patent engineer, so I will stop at that. The method has been validated in very different conditions. I can say that I'm very confident that we can do our method in all right now single-family housing, and this is the problem. Not that our method cannot work in other housing; it's just that it has not been really done yet. So the next steps that we want to do, especially in the coming months, or both going into the collective housing situation, multifamily houses or small buildings, big buildings if needed. The main problem for us is getting the cases to study. We managed to get a few houses to test, but the buildings are more difficult to find these days. The other thing is the method acceleration. I know that a cube method is faster than other methods, but we still think that it would be better if it could be done in one night only. And I would like now to be able to say that in one night tests are possible. I did not talk about them in this presentation, but I am very confident in saying that the results are as good as the results we get in 2 nights. But there is a but. There are more experimental constraints. So this is mainly why I didn't want to talk about it, because explaining all the constraints and the theoretical reasons behind these constraints is a bit complex. So I will try first to explain that to my colleagues from the Annex 58 and exchange with them before opening up to the exterior world. Besides, the validation process is not entirely finished. we still have to do a few coding tests to make a reference value for the houses on which we had a lot of quick cube measurements. So it's almost finished, but I'm very confident to say that it actually works, and we can make very good estimation of the heat loss coefficient in only one night. This being done, I think it will be even easier for us to go into the collective housing. We don't think there's any theoretical problem in doing the same test in buildings or multifamily houses. It's more the opposite. We have several ways we could do it, and we haven't been able yet to experimentally determine which one is the best, mainly because of the lack of experimental reference cases. But it's something we're working on these days, so hopefully in the coming months, I will both be able to explain our method, how to do it in one night, and how it works on collective housing. And if I'm not completely wrong, this is the end of my presentation. I thank you for listening to it, and I'm ready for any question. Thank you.